Welcome back. So today we're continuing in our unit. We finished up talking about the galaxies and branched out, took a look at the variety and the classification of galaxies, their origin and kind of evolution. And now we want to shift gears and take a look in chapter 14 at modern cosmology. Cosmology in the 21st century, some of our most up-to-date information of technology and our understanding of the universe as a whole. And so our what are we summary for today is we are products. So we actually are products of two cosmological processes of gravitational kind of collapse and nuclear fusion in the stars, nuclear fusion. So between these kind of gravitational collapse and nuclear fusion, we are the products of these cosmological processes, is sort of what the what are we summary is for this chapter. So this chapter is going to focus in on the universe as a whole, the nature of the universe, its origin, and kind of what the future might hold for our universe. And so a lot of this information is theoretical. However, we do have a fantastic study that we'll talk about towards the end that really solved a lot of questions that we've had about our universe, which seems amazing that we can even come up with some of these ideas, let alone get some evidence for these. So let's get started on that. So cosmology, that term for it, is the study of the universe as a whole. So its nature, its origin, and its evolution as well. So where our matter came from and where it's going, basically. So yeah, and it is kind of fun to think about space stretching like a rubber kind of a sheet sort of thing, and an invisible type of energy, sort of repulsive type of a force, balancing the attractive force of gravity in there, in that the fabric of the universe actually can expand or contract, sort of thing. So it can be kind of mind-bending, but we do need to kind of maybe go through some misconceptions that we might have. We do want to start by kind of clearing up some things so that we aren't misled by some of our misconceptions that we might have about it. This first one they talk about is called the edge center problem. And so the universe has no edge and it has no center, which is difficult for us to kind of envision because in our daily lives we're kind of accustomed to having boundaries, walls, edges to our pizzas and that kind of things, and centers. So it's natural for us to kind of think that the universe would have an edge or a center to it, but that can't be right. So we do want to make sure we change that in our minds. I mean, they're just saying, well, you know, what if you kind of went to the edge of the universe? What would you find there? A wall, a great empty space? Would there be nothing there? And I do have to admit that when I first started studying about this, that I kind of thought, well, what if we went to the edge of it? But we can't. We've got to make sure that we don't think that way so that it doesn't mislead us, because that would be like the end of space itself. So, you know, and you can't kind of reach past that. So we do want to make sure that we don't be misled by thinking in that way. So modern observations indicate that the universe could be infinite in size, and so it would definitely have no edge to it, and therefore no center to it as well. Okay, so we want to make sure we take care to avoid thinking that the universe has a center or an edge. Okay, now the necessity of a beginning. They're mentioning here a conflict between observation and theory, and so this reasonable kind of observation that we have that the night sky is dark Well, this question or this conflict here is called Olber's paradox. After Heinrich Olbers, they're talking about here, an Austrian physicist, sorry, and astronomer. In 1826, he was the first to kind of propose this question. You know, if the universe is infinite, the night sky should never get dark, okay, was his idea. And so let's kind of look at what he was meaning by this. So if we assume the universe is infinite and filled with stars, kind of like being in a forest, when you're deep in a forest, any kind of direction you would look, your eyesight would end up on a tree. Well, that's what they're saying, is that any which way you would look in the universe, your eyesight would end up on a star. And so the sky should just be this blindingly bright glow because of all the stars, the infinite kind of universe of stars. And so why does the night sky get dark? Okay, and so sort of so it's like any which way you would look, it would end up on a star. And so it shouldn't get dark at night is what Olber was proposing in here. And so the answer to Olber's question actually was first suggested by Edgar Allan Poe in 1848, where he proposed that the night sky was dark because the universe was not infinitely old, right? It might be infinite in its extent, but it's not infinitely old. It had a beginning, okay? So in some time in the past, it had a beginning. So the more distant stars, they're so far away that the light has not reached the Earth yet. And we talked a little bit about this when we were looking at our galaxies. Some of those most distant galaxies, if you remember, that, you know, some onwards of 10 billion light years away, we were looking at the universe at a much younger time. And so if you go back even farther than that, perhaps even farther than the age of the universe, well, that light hasn't made its way to the Earth yet, okay? So if you looked far enough back, the look back time becomes so great, it's actually greater than the age of the universe. So this implies then that the night sky gets dark, okay, because the universe had a beginning, okay? And so that's sort of the resolution of Olber's paradox in there. It had a beginning. It is not infinite in age. Okay. Okay. Very powerful idea, and it does illustrate the difference between the universe and the observable universe. As I mentioned, kind of with the galaxies, it's like, okay, 10 billion light years away, but there could be things a little further, but yet that light hasn't made it to us to where, you know, we can observe that. So that's kind of a distinction. The universe is everything that exists, but the observable universe is the part that we can see. So the universe is about 14 billion years old, and we'll refine that just a little bit towards the end. But the observable universe kind of has that radius of 14 billion light years, okay, in there. So observable universe, finite, but the universe as a whole could definitely be infinite, okay, in size, okay, in there. Okay, so cosmic expansion, and we did kind of allude to this with the redshifts that we talked about, Hubble's law. And so he was very influential in getting that relationship between the type 1A supernova redshifts and distance. If you remember that, sort of those recessional kind of velocities relating to distance. And so in 1929, he published his discovery that the sizes of the galaxy redshifts are proportional to a galaxy's distance. And that was like the highest rung on our extragalactic distance ladder, if you remember that. So that kind of meant that nearby galaxies had small redshifts, and very distant galaxies had even greater redshifts. So implying that the redshifts do imply that these galaxies are receding from one another, because as they're traveling through their rays that finally make it to the Earth, as they're traveling through the fabric of space-time, the fabric of the universe, it's expanding, and those waves will get elongated or stretched, so to longer wavelengths, so redshifted. So yeah, he was the one that kind of realized that the universe is expanding. So, and this is just kind of going through several galaxies in different clusters, different distances, that did show that variation in the redshifts. So there's several pictures here that they take us through. Okay. And continuing to kind of take you through those that are farther away have the greater redshifts to them. So now the expansion of the universe does not imply, there's actually a typo on your PowerPoint here, it's correct in your book, it does not imply that Earth is at the center of this expansion, okay? And they give this sort of analogy to baking raisin bread. So the dough is rising, it's pushing the raisins away from each other uniformly at velocities that are proportional to their distance from each other, right? So two raisins originally close together are pushed apart kind of slowly. Two raisins farther apart are pushed apart even faster, so meaning that those galaxies that are farther away are receding even faster. That was sort of his relationship that he came up with, Hubble did. And so we would kind of conclude that the universe is expanding uniformly all around. And it didn't matter, you know, which raisin kind of you were on. A little bacterial astronomer they talk about, they get a little silly. They would get the same Hubble law. No raisin had any special viewpoint, okay? So there was no center to this expansion. It expanded everywhere. And so no galaxy has a special kind of viewpoint. And so this idea that there is no center does make good sense with the cosmic expansion that's happening. Okay, so, and of course that ends when you start thinking about the crust of the bread. So the universe cannot have an edge, and it does not have any center. So there is no center to the expansion. Okay. So this brought us kind of to a theory, a process that led us to the Big Bang theory, that expansion of the universe, to conclude that the universe must have begun with an event of astounding cosmic intensity, right? So a very hot, dense state, kind of like the song, the Big Bang theory song goes, that the expansion began. So what they're doing is saying, imagine we have a video of the expanding universe, but then we run it backwards, okay? So we'd see the galaxies moving towards each other, but since there is no center to the expansion, you wouldn't see them coming into a single point, sort of thing. I also kind of have a balloon analogy. Let me see if I can get that to show up for you on this expansion sort of thing. How well you're going to see that, I'm not sure, but let me scroll up here for a second. So, expanding kind of balloon analogy. The photons that are released from every little yellow thing on here is a galaxy. Okay. Galaxy, a galaxy, a galaxy, 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 galaxy sort of thing. On this one here, we have a much smaller universe, our balloon here, and everything is traveling, the wavelengths are traveling, but they're traveling in the blue wavelength, so a shorter wavelength. Well, over time, as the galaxies, the universe, the fabric of the universe expands, it's going to stretch those wavelengths into longer wavelengths, and so that's why you're seeing the red on here. But notice that your galaxies have not been stretched. It's the space-time, the fabric of the universe that's doing the expanding, okay? And so let's pretend that on our balloon, we've taped some pennies or some coins on it, okay? And so the size of the penny is not going to change as we blow up the balloon, right? And the expansion is happening. But this one here is kind of showing all the galaxies tend to still have their same positions, but the fabric between them is what is being expanded. And so this one's kind of taking you through the blue, very short wavelengths, and then it kind of goes to green, and then it ends up going to red as that expansion kind of continues in there. And so this is just trying to do a balloon analogy where the fabric of the universe is doing the stretching and the expanding in there. So, oh, I think I'm still there. Okay. Okay, so with the galaxies kind of approaching, you wouldn't see them approaching a single point though, because there is no center to that expansion. It's just every little part of it is expanding. So the space in there just kind of disappearing, okay? And they're kind of still in their same neighborhood. The distances between the galaxies would decrease without the galaxies themselves doing the moving, okay? So galaxies would just kind of begin to merge. If you ran it that far enough, you would end up with the matter and the energy of the universe being compressed into this extremely high density, high temperature state. And so we can conclude that the expanding universe began with an expansion from that very high density, high temperature state. Okay? Expansion began in this. And so modern astronomers call that the Big Bang. Not that it was an explosion, but that it was an expansion of these space-time in there. So that's sort of the Big Bang. So how long ago did the universe begin? And so to find the age of the universe, you would want to divide the distance between the galaxies by the speed with which they are separating. And then you can find out how much time was required for them to have reached their present kind of separation thing. We actually use what we call Hubble time. So again, the namesake of Hubble. And it is based on the Hubble constant that we talked about last time, which is roughly 70, I mean, give or take, plus or minus on that for it. But these basic kind of observations of the recession of the galaxy require that the universe began with a Big Bang about 14 billion years ago. And we'll refine that towards the end with a study that was done. So the look back time makes it possible to observe the Big Bang directly, being able to look at very, very distant galaxies. And it happened everywhere, okay, in there. So look back time to nearby galaxies is only a few million years. Some of those more distant galaxies, remember those quasars we kind of talked about? That becomes a large fraction of the age of the universe. So if we look between and beyond even those most distant observable galaxies, we should kind of be able to detect that very hot kind of dense state. So the hot gas that filled the universe long ago, those 14 billion years ago, that hot dense state. And again, we don't have an edge or a center when we think about that. And galaxies are not flying apart, they're not being torn apart, it's just, they're in their basic same locations, except the fabric of the universe has expanded in between. between them. So they're not being ripped apart kind of thing. Okay, so it didn't occur in just a single place. It occurred everywhere, this Big Bang. So everywhere, including right where we are right now, that hot, dense state. So the idea that we should still be able to see some sort of remnants from that. So yeah, whatever direction we kind of look at great distances, they can see back to the age when the universe was filled with that hot, kind of dense gas in it. So this sort of background radiation in there. As we continue to look, so now we've got, you know, all of our galaxies in here. And so if we looked even beyond that just a little bit, this pinky, mottled kind of pink color from that beginning hot, dense state, we should be able to see, okay, the rays, electromagnetic radiation rays that came from that very hot, dense state. And amazingly, they have found this. They call it the cosmic background radiation, or it's actually microwave radiation, so CMB, cosmic microwave background radiation. And this is evidence for the Big Bang. And so we can't, of course, see it with our eyes because, again, that has traveled as the universe was expanding. And so those wavelengths have been redshifted into the far infrared and even radio wavelengths of the electromagnetic spectrum now. And so, you know, visually we can't see them, but we can detect them in infrared radiation and radio telescopes that can detect that. So amazingly, we can detect that radiation from the Big Bang, okay? And that is truly amazing. And they're saying here that the radiation from that hot gas of the Big Bang is calculated to have a redshift of 1100. So it has really stretched over time for its wavelengths. So it was very short wave electromagnetic radiation when it began, but because of the expansion of the universe, it has been redshifted to these much longer wavelengths of the far infrared and radio wavelengths. And they have detected these. And so in 1960, we had a couple physicists that were measuring radio brightness on the sky, okay? And they discovered this peculiar radio noise. So they were detecting this radio waves, and they didn't really know what it was, though. But in 1940, you know, 20 years earlier, a couple physicists had predicted that there should be this black body radiation that was emitted during the Big Bang, okay, that should now be redshifted to the far infrared and the radio wavelengths. So they theoretically predicted that we should see this. And so in the 60s, we had a couple other physicists that built a receiver to try to detect this. So they were setting about, we had theory, now we wanted to try to get some actual observations, and they set about to try to detect those. Well, when these two guys heard about that, they're like, what if that's what we've detected, this strange, peculiar radio noise? They realized that they had detected the what we call cosmic microwave background radiation. So that is actually the radiation from the Big Bang, that hot, dense state. And so these guys were the ones that won the Nobel Prize in 1978 for that. So it's kind of like those other guys were just a little bit too slow, but they just kind of accidentally found it. But once they learned about the work, they were like, we've got it, this is what it is. And so yeah, they won the prize for that. But that is tremendously exciting that we do have the remnants, that we can still detect the Big Bang, the cosmic microwave radiation from that. So that was extremely exciting from that. And so they're just talking about just how far it had been redshifted and what its temperature would kind of be now. And so they're saying that initially it would have been about 3,000 Kelvin, and now those wavelengths have stretched so much that now we're at about 2.7 plus or minus Kelvin. So it had been effectively redshifted, or those wavelengths, to longer wavelengths, that now it's at a much cooler kind of temperature here. And so they have been able to confirm that with measurements, that the cosmic microwave background is black body radiation with a 2.7 Kelvin temperature to it, and that's in very good agreement with the theoretical predictions that they had for it. So it may seem strange that the hot gas of the Big Bang seems to just have a 2.7 Kelvin temperature, but that is a tremendous redshift, and that is why. I mean, it has been expanding for 14 billion years. That light has on its way to Earth, so a redshift of about 1100 is what they talk about there. So yeah, the gas clouds that emitted those photons initially had a temperature of 3,000 Kelvin, but because of the expansion of the universe, right, it had been redshifted to much longer wavelength, is their idea on that. So that is why the hot gas of the Big Bang seems to be 1,100 times cooler now, okay, because of the redshift and the expansion of the universe. Okay, so here we are. We are going to, I'm going to probably flip through a lot of these pretty rapidly, but it's taking you through the fraction of a second to the first few seconds to minutes, and then we get into thousands of years and so forth of the Big Bang. But when we start out, we're talking about particles and nucleosynthesis, so where we're starting to just put together the four forces of nature, so gravity, electromagnetic radiation, strong and weak nuclear forces, and how those are just beginning to separate, kind of thing, and then the formation of protons, neutrons, electrons, and atomic nuclei, this sort of thing. So it's trying to take you through just fractions of seconds and minutes and that kind of thing. So I won't go through every single detail, but we'll go through a little bit of it. So, okay, so that cosmic microwave background is evidence, very clear evidence, that conditions at the beginning of the universe were very hot and very dense, okay? So we can kind of combine that and the observations with the knowledge of physics on how the atoms and the subatomic particles behave to work out the story of the Big Bang, okay? Now, it is important to note here that cosmologists cannot begin their history of the Big Bang at time 0, okay? So it's going to be a fraction of a second after time 0. So what they're saying here, no one understands the physics of matter and energy at such extreme conditions. So we're going to go a fraction of a second after that. So we're getting amazingly close to the beginning there. Okay, so in that tenth of a millionth of a second, I mean fraction of a second, okay, we're going to have the high energy photons, very dense state. So we've got a black body temperature well over 1 trillion Kelvin, extremely hot, and a density greater than 5 times 10 to the 13th grams per centimeter cube. Very dense, okay? So this is nearly the density of an atomic nucleus, okay, of an atom, a nucleus of an atom. So if photons have enough energy, 2 photons can combine and kind of convert their energy into a pair of particles. One we call normal matter, the other one we call antimatter. And it's like you could have protons and antiprotons, neutrons, antineutrons, electrons, anti-electrons. So normal matter and then the antimatter, they call it. But when antimatter particle meets its matching normal matter particle, the two particles annihilate each other and convert their mass back to energy. So when a proton and an antiproton collide, they release gamma rays, energy, and so they're kind of flitting back and forth between sort of particles and energy, flickering kind of back and forth. So yeah, two particles come together, normal and anti particle, annihilate each other and convert their mass back to energy. So mass and energy are equivalent in Einstein's relationship, and in the form of two gamma rays. So we have a time where things are flitting kind of back and forth between particles and energy, and vice versa there. So yeah, proton, antiproton collide, they destroy each other and produce this energy in the form of gamma rays. So this is like very early on, okay? And so photons had enough energy to produce a proton and an antiproton and neutrons and antineutron pairs, and they went back and forth, back and forth. All the while, so we do get that flickering of energy back and forth, okay? The expansion of the universe is occurring, and it's beginning to cool slightly, okay? The radiation is cooling a little bit. So temperature has fallen, 10 to the 12th kind of Kelvin, still very hot as we're going along. So the first few seconds and minutes in here, let's see, all the protons and neutrons would have annihilated their antiparticles, and for some reason the antimatter is very, very low and normal matter kind of dominated in this. So, we live in a world of normal matter now, and antimatter is extremely rare. So that flickering back and forth and seemed like the normal matter kind of won out with this, okay? And then electrons and positron pairs could still be produced because they're extremely low mass. But that all kind of continued, and here we are only at about, 4 seconds after the universe. And again, we're expanding just enough that it cooled the gamma rays to where they could no longer make even the electrons and the positrons in there. And so here we have where normal electrons kind of survived. So now we have our protons, neutrons, and electrons formed, of which, of course, the universe is made of, just within the first 4 seconds of the history of the universe. Okay, so we got this soup of hot gas and radiation that's continuing to kind of cool. A couple minutes old, so now we're only just a couple minutes old. And the protons and neutrons could finally form. So a proton and a neutron kind of making an atomic nucleus. So cooled enough to bring those together, and to where we have some hydrogen forming, right? One proton, one neutron forming the hydrogen atom. So in the beginning then, that formation of hydrogen, that's why we see so much hydrogen in the universe, right? Mostly hydrogen, and then a little bit of helium came along as well. So yeah, after kind of the next few minutes, further reactions began converting that heavy kind of hydrogen into helium, okay? But almost no heavier atoms could be formed at that time. Remember, that's going to take getting cooked up in our stars. Our stars haven't formed yet. Okay, so that's just a couple minutes after that. Okay, so continuing to cool, 3 minutes. By about 3 minutes, it had become cool enough so that most nuclear reactions had stopped. By the time it was 30 minutes, the reactions stopped altogether. About 25% of that mass then was in the form of helium, okay, of the helium nuclei, and so that 75% was the hydrogen, and that is the ratio that we do still see even in our stars, right? mostly hydrogen, a little bit of helium. So that is still what we do see in our universe as a whole now, beginning in what, just about 30 minutes old. So the hydrogen and the helium that we observe in our oldest stars originated from this Big Bang very early on. Okay, first few minutes of the universe. Hydrogen in the water, right? Molecules in our body have survived unchanged since the formed in those first few moments of the origin of the universe, the Big Bang. Okay, so we are definitely, stardust and Milky Way children and of the universe. We're very much part of it. Okay, and so if you remember, then the heavier elements get built up in stars, which we don't have any stars yet. And of course, later generations of stars. You needed to enrich the interstellar kind of dust material as massive stars lived and they died and spewed that out. So that took much longer to get heavier than helium atoms in there. So initially, yeah, the universe was very hot, that it was totally ionized, and so electrons, they weren't attached to the proton and neutron nuclei, right? They're out there doing their own thing. They weren't attached to them yet, okay? So these free electrons just kind of flitted all over the place, and they would run into, they couldn't really travel very far before they encountered, another electron, and it was deflected kind of thing. But as the universe continued to kind of expand, okay, we were starting to get a little bit lower density. It's still an ionized gas though, so the electrons were still not captured. And so now, on this one, neutral gas after what we call recombination, or really combination for the very first time, where the nucleus, protons and neutrons, could finally capture their electron, okay? And it's called recombination. Really, combination for the first time is better. And now that radiation can escape. It's more transparent now, so those wavelengths can go through, and that's what they're saying. That's the evidence of the cosmic microwave background radiation that we see now. So the evidence of that hot, dense state. Those are the wavelengths that began right after recombination, the nucleus capturing their electrons. And so that is where those wavelengths began, and of course now those have been stretched and with the expansion of the universe to a much cooler temperature, but that temperature in there about 3,000 Kelvin when it started, and much shorter wavelengths have now been red-shifted to much longer wavelengths and a much cooler temperature as well. But that's where that cosmic microwave background radiation starts from. Okay. Let's see, I kind of think we're good on this. So now first thousands and millions of years now, but those photons became less and less density of the gas. Matter couldn't quite clump together yet because of this photons kind of smoothing out the gas as they went through. It was very transparent in there. And here's that term, recombination. So the density decreased, falling temperatures until, so we finally got to 3,000 Kelvin, and they were able to capture their electrons, okay, after that. So that's known as recombination, forming the neutral kind of hydrogen in there. Okay. So these are what we're seeing as the cosmic microwave background with the large red shifts that make their temperature now about 2.7 Kelvin. So good evidence that the Big Bang did occur. Okay. They detected that. Very interesting. Oh, they keep going on here. Recombination left the gas of the Big Bang neutral, still hot, dense, but transparent, so the light could get through. It came here as the universe expanded and cooled. Kind of that glow faded, and they say we entered kind of a dark age in there. hundreds of millions of years until the formation of the first stars. So we were able to get enough clumping together of the matter, attraction of gravity, pulling it together to get enough density that we could then get our first stars to be born, and then burst forth the light from that. And so reionization of the universe. So when we look back to our most distant quasars, right, those active galactic nuclei, and our galaxies, we can see the traces then of that beginning ionization, really called reionization, ionization for the first time, of the universe, okay, when our first stars were being born and our galaxies being born. So very interesting how this kind of runs here. Initially, you probably can't see this very well, but radiation dominates at the beginning, so that's like 1 second, 1 minute, 1 hour, 1 day, 1 year, and so forth. As we go through time here, what the temperature was, noticing how it's cooling down as we go. But we were pretty much radiation dominated for a period of time. So energy density equals matter density. Then they became a little bit equivalent, energy and density, energy and matter. And then now we're in a matter-dominated universe. So we went from a radiation or energy-dominated to a matter-dominated universe. Okay, so recombination happening here, reionization, so the first stars in the galaxies here, and there we are now, they're saying, in this little diagram here. Okay. And how that kind of changed over time. So space-time, right, the fabric of the universe, matter and energy here. So how can the Big Bang have happened everywhere is the question here. We want to look at how the universe does look essentially the same in any direction that you would look out. And so this is known as isotropy, right here, isotropy. Of course, there are some local differences, but if you look toward a galaxy cluster, okay, you would see more galaxy clusters in the fact that on the largest distances, the universe looks the same in any direction you would look, is what isotropy indicates, in all directions, so isotropy. And this is actually what we see in the cosmic microwave background radiation. It is the same in any direction that we do look, okay? So same direction is isotropy. Homogeneity, on the other hand, is saying that the universe looks the same from any location that you happen to be in. And so some regions might contain a little more galaxies, some a little less, but at a very large look-back time, this is what we're going to see, that the universe, any place you might be, if I'm on that galaxy over there or a different galaxy over there, that the universe will look the same on a very large scale from any location in the universe, okay? And so that is kind of seen in our distribution of our galaxies and our galaxy clusters when we're looking very large scale at the universe. That's known as homogeneity, that it looks uniform or the same at any location we might be looking from, okay? Which we can only look from our galaxy. But the idea of this is that it would look the same everywhere, no matter what galaxy you were on, from any location. Homogeneity. And together, isotropy and homogeneity, or being homogeneous throughout, leads us to what we call the cosmological principle. The assumption that any observer in any galaxy sees the universe, the same general features, that it is isotropic and homogeneous throughout. So doesn't matter what direction we're looking or from what, say, galaxy or location we're looking, that is uniform throughout. Okay, and so that's the cosmological principle in its major features. So we're talking about on the largest scales. I think way back in chapter 1, we talked about scale. That. Okay, so it does imply that there are no special places in the universe. So that's, leading us, no center, no edge. There are no special places. Kind of reiterates that there. Of course, because a center and an edge would be a special place, and there are no special places in our cosmological principles. So what we see from the Milky Way should be very typical of what any other intelligent creature from any other galaxy would see of the universe on its largest scale. Okay. Cosmic redshift, so again we are talking about those redshifts to longer wavelengths. Distance is the separation between 2 points in space. Time is the separation between 2 events. So in Einstein's theories of special relativity and general relativity in 1905 and 1916, respectively there, he describes how space and time are related and can be considered together as the fabric of the universe. So that space-time term comes from Einstein's studies, and that's known as space-time, and that's what we'll kind of think of as space-time as the canvas on which the universe was sort of painted or is on, and that the space-time can actually potentially contract or expand. And so in Einstein's theories, it does predict that there can be an expansion or there can be a contraction of space-time. Now Einstein at the time there was of this idea of a static or steady state universe. So he was thinking, okay, those two things were in balance. The contraction of the pull of gravity, that attractive force, and the repulsive expansion force, that those were balanced, and it was a static or a steady state universe, okay, is what Einstein had thought in that. And the stretching of space-time really does explain the cosmological redshifts, right? So basically our galaxies are at rest in their positions, but that space-time is doing the expansion, right? And so as space-time is stretching or expanding, a little photon that's working its way through the expanding universe is going to get stretched as it continues to longer wavelengths, right? So here we have sort of a very short wavelength at a very distant galaxy there. So they got it in the purple color. That's a very short wavelength. And it starts to make its way, that radiation starting to make its way toward our galaxy. Over time, the expansion of space-time expanding stretches out that wavelength, right? So now it's starting to be the color blue. It's getting towards longer wavelengths. And here we've got a yellow. Farther it travels, it has to travel, and it's stretching more. And then, so yellow. And then red here, it arrives at our galaxy at a much longer wavelength. So it has, in essence, what we call redshift. And that redshift is proportional to the distance that it traveled. So this was a lot of what Hubble came up with Hubble's law, right? The redshifts, and then that being proportional to the distance, the highest kind of rung on our extragalactic distance ladder. So this idea of cosmic redshift, and you know, Einstein was of the thought that it wasn't expanding, though. Keep that in mind. He was like, no, we're steady state. It can contract and it can expand, but it's not doing that. It's balanced, okay, is what he thought in his theories in there. So yes, these sort of redshifts of the galaxies are apparent shifts, right, of recession of these moving away from us. So apparent recessional kind of velocities that they talk about. Okay, so Hubble law does apply with these redshifts, as we mentioned, and they can be used to estimate the distances to galaxies. So that highest rung on our distance ladder is what we kind of mentioned that last time, that Hubble was able to work through. So almost immediately after Einstein had published his theories, theorists were able to solve the highly sophisticated mathematics to compute descriptions of that behavior of space-time and matter. And so they arrived at some model universes. We'll talk about 3 model universes that pretty much dominated the 20th century. And of course the equations allowed for 3 general possibilities here. Space-time might be curved in ways that are called a closed universe or an open universe. If we had space-time that had no overall curvature, meaning a flat curvature, zero curvature, it was known as a flat universe in here. Okay, so basically 3 kind of models that we come up with: an open universe, closed universe, or a flat universe. And these all depended on a value in Einstein's theories called the critical density. Okay, was the actual density of the universe greater than, less than, or exactly equal to this critical density? And the critical density is the density that the universe would have to have in order to create no curvature, zero curvature, or a flat universe. So the actual density in the universe would have to be equal to the critical density in Einstein's calculations for us to have a flat universe or zero curvature. Okay, it's kind of what this is going to take us through here. Okay, so flat does not mean 2-dimensional. It just means that our familiar rules, our Euclidean rules of geometry that we learned in grade school, you know, the angles of a triangle, the geometry kind of that we learned in elementary school, remains true and holds true even on the largest scales in the universe. Okay, that's what we're considering flat, meaning no curvature, okay, in there. So if we had different rules of geometry, these would apply if we had a curved kind of universe, okay, on large scales in there. Thankfully, we're going to find out that we don't have to try to wrap our brains around a different type of geometry. So the main criteria separating those, as I mentioned, was the average density of the universe. And according to the general relativity theory that he had, this would determine the overall curvature of space-time. So the average density of matter and energy, okay, if it were equal to that, as I mentioned before, space-time would be flat. So the critical density that Einstein calculated was 9 times 10 to the minus 30th grams per centimeter cubed for density. And of course that is gauged on the Hubble constant value, the exact value of that, okay, in the calculation. And so if the average density is more than the critical density, and I might write some of this up on the board for us. So these would be the model universes. We're going to talk about open first here. Open universe. Less than the critical density. So CD, the critical density of that value we had just before there for you. And we would end up with a infinite, it would be an infinite universe. Okay. And let's see. I'm going to try to draw something here. Where you kind of get this hyperbole type of a shape, hyperbolic type of a shape. Kind of a shape, which would end up kind of looking like a saddle kind of curvature. If it was less than the critical density, it would be an infinite structure in there. And so if it is less, that the universe must be open, what they call it, an open universe. Okay. If we had what we call a closed universe, we have more than the critical density. Okay. And the universe would be finite. Okay. And we would have sort of this elliptical thing, but that it sort of closes back in on itself. So sort of an elliptical sort of shape. Two-dimensional kind of shape for a closed, okay, and that would be more than the critical density. If somehow we had the universe where the critical, the density of the universe was exactly equal to the critical density, we would have what we called a flat universe. Third one, a flat universe. Okay, flat, and this would be equal to the critical density. Of course, you would get an infinite universe in that case as well, but here it is just going to go on and on and on. Okay. As such, and this is what we call Euclidean. Okay, has no curvature whatsoever, so a flat. And that the normal Euclidean geometry holds, even at the largest scale in the universe. What I have here is a couple pictures, kind of looking at the shape. Different shapes that we have here. So the first one here, this would be if the critical density equaled the average density of the actual universe density. So we would have zero curvature, and then looking at your triangle here, this is Euclidean space. So it follows our normal geometry. You see how the triangle has the normal degrees of angle, so that's known as zero curvature or a flat universe. In the closed one, so say we had more than the critical density, it sort of closes in on itself, positive kind of curvature, elliptical space, okay? Elliptical space, it closes kind of back in on itself. Notice how that triangle looks. Those angles are larger than the normal angles of a triangle, okay? And that would be a closed version. In this one, our open version, the hyperbolic space, see how that kind of looks like a saddle, negative curvature. Notice how those are smaller angles than the normal geometry. So less than the critical density. And these are the shapes for curvature of the universe. Three models that really dominated the 20th century, and each kind of category there had its fans that they thought was the true kind of shape or curvature of the universe. But the key thing was, well, what is the actual density of the universe? Okay, so they had to set about to try to figure out what that actual density of the universe was. Okay, so that kind of takes you through the same thing I was talking there. So the Hubble time is actually the age the universe would be if it were totally open, going on forever, totally open kind of thing. that would mean that it would have to contain almost no matter at all. But if the universe is flat, then its average density must, of course, be equal to the critical density. But the problem was when astronomers tried to add up all the matter that they could find, right? All the normal matter, so you and me, you know, protons and neutrons, all the normal type of matter, it only added up to just a few percent, about 4% of that critical density, right? So just a few percent of that. And then they got to thinking about that dark matter. Remember the non-luminous matter that we have talked about several times before when we talked about our galaxies and how they came to the realization that our galaxies actually had more mass than what was predicted. And so what could have been that? And they come up with the dark matter, the non-luminous matter. So they were thinking, well, could that dark matter then make up the rest? So yeah, when we talked about our galaxies, the gravitational fields were much stronger than what was anticipated, right? And so that got into thinking about the dark matter, but non-luminous, right? But even when you added in the non-luminous matter, okay, we ended up not having enough. So they're thinking dark matter might contribute to about another, 24% in there, okay? So galaxies do contain the dark matter, as we learned, and in fact it was much more dark matter than normal matter, if you remember that. So they've got this term here for normal matter, we call it baryons, okay? That's normal matter. And this should look familiar. This was that one where we looked at, when we were trying to get at the masses of galaxies, that orbital velocity versus the radius and the Keplerian motion, that it didn't follow the Keplerian motion. That's how we knew we had more mass in our galaxies, and that prompted the dark matter idea. But normal matter was called baryonic, or baryons, and so non-baryonic would be our dark matter, okay? And they're just kind of going through, the dark matter was the non-baryonic matter, and then they're thinking, well, it's not just dark matter, it had to be cold dark matter, meaning it moved a little slower so that things could actually start to clump in the universe to create our galaxies. So a little distinction there with cold dark matter. I'm in there. So here we go. That's still only almost, 30% in there. So 23 dark matter, 4% normal, only about a third of the critical density that we needed, right? So not really more than 30% in there. So the universe has more than normal matter and dark matter. There is quite a bit more out there, even more than dark matter. Okay, 70% of this. Okay, and they're going to get to that here in a second. But yeah, so 21st century began, cosmologists made a startling discovery, and so we want to kind of look back up just a little bit to a couple problems that they encountered in 1980s, and we're almost certain that we're the flat one here, but we got to get to this first here. But a couple problems with the Big Bang theory in general was this kind of flatness problem was one of them, and the other in there was kind of this horizon problem that they were talking about. But the flatness problem, the curvature of space-time seems to be near the transition between an open and a closed universe. Kind of in between there. It seems to be approximately flat. And so they're thinking, well, now how could it have possibly been flat, at that hot, dense kind of state there? So why is it so exactly flat with no space-time curvature at the time of the the Big Bang. And so you see that term up there, inflation. Yes, we had an expansion going on, an inflation happening. But here's where they're thinking there was an extra bit of inflation. So an extra expansion in the universe that could kind of explain the flatness problem. And then the horizon problem. So when astronomers kind of correct for the motion of Earth, they find that the cosmic microwave background is very isotropic. I mean, it looks the same, homogeneous in any direction we might look, right? So at the beginning then, how could background radiation be coming from two separated points within the Big Bang kind of thing? And again, if they do the extra expansion, it would account for that. So, and kind of smoothed it out. So every part of the observable universe became kind of that same temperature because of this extra expansion. So they had to modify just a little bit their initial Big Bang theory to include now what we call the inflationary Big Bang. And this is how science works. You know, if your theory is not matching your observations, then you tweak it, right? You've got to go back and tweak it. This theory predicts that there was this sudden extra expansion in the universe when it was very young, and that it was even more extreme than predicted by the original Big Bang. And so it would have smoothed everything out, would have flattened out the curvature, would have uniformed the temperature throughout in there. And so that, inflationary model kind of made things match a little better between theory and the observations that we have. So now we've got a universe that's most perfectly flat space-time geometry because of that sudden inflammation long ago. Okay, and so they do think we're here with this one, but we got to find out what the rest of that mass, where it is, what happened to the rest of that mass kind of thing. Perfectly flat kind of a universe in there. So, where is it? What could be weirder than even dark matter? Normal matter, dark matter, what's weirder than dark matter? Well, we're going to get to that. Here we go. If the density of the matter is less than the critical density, expansion should kind of be slowing slightly and the universe would expand forever kind of thing. If the density of the matter is greater than the critical density, well, that's just going to kind of almost go back in on itself, right? Close down and maybe even start contracting again. Start going back the other way instead of expanding, sort of thing, if we had that option in there. And so the acceleration of the universe. Here, astronomers were kind of struggling to measure the distances to very distant galaxies. That's a hard measurement to get at. But we want to compare their distances with redshifts and kind of, see if we could detect an expansion or a slowing of the expansion or an extra expansion happening. And so the kind of key project for the Hubble Space Telescope was to kind of figure out that rate of expanding, or did we see a slowing of the expansion? And several teams kind of got together and were trying to be the ones that discovered this. And that crazy thing they actually found is that it's not slowing at all. It's actually speeding up. It's accelerating. Acceleration of the universe. But what they were doing was they were looking at those type 1a supernova, those standard candles, right? We also talked about the Cepheid variables being those standard candles in there. So we got, a few nearby galaxies that we had the Cepheid variables in. Could definitely help us anytime we got a type 1 supernova, type 1a supernova, if you remember those, kind of standard bomb kind of things, because they're so bright. We could see those from farther galaxies in there. And so they were learning about those redshifts in there. And both teams together in 1998 agreed that, well, the expansion of the universe is not slowing down, it's speeding up. So there is an acceleration in the expansion of the universe. It's accelerating in there. Okay. Yeah, so this was kind of a very exciting thing. The supernova kind of appeared fainter than expected at very large redshifts. And so this kind of prompted them then that there must be something out there causing this acceleration in the expansion, some sort of a repulsive force in the universe. And so it kind of began this idea that dark energy might be this force in there that is creating the repulsion that's driving the acceleration out there. So it just sort of got them to thinking about, well, where is this extra matter kind of coming from, this critical density that we need to try to get at. So also that expansion is accelerating, and there must be a force of repulsion that's driving it, all right? And so trying to understand it, what it could be, and it led back to Albert Einstein. If you remember, in his theories, he had put in this, his idea was that the universe wasn't expanding and it wasn't contracting, it was steady state. So he put in his mathematical equations in there, a cosmological constant, we call it, that it is actually a repulsive force against gravity, right? Because gravity wants to contract things, but he also said that space-time could expand, and so he put in a repulsive force to balance out the gravity, the contraction of gravity. So he actually put in what we call a cosmological constant. He wanted to keep a steady state in there. So he needed to balance the attractive force of gravity. And so it brings us kind of back to Einstein's work. That cosmological constant is representing a force of repulsion that would make the universe hold still, right? He was steady state idea. But, you know, in that time, 13 years later, Edwin Hubble in 1929 said, no, the universe is expanding. Sorry, Albert, the universe is expanding, right? Oh my gosh. That was like, he thought, oh gosh, that was the biggest blunder of his career, that he put in that repulsive force. Okay. Well, you know, to keep it steady state kind of thing. Astronomers aren't quite so sure that he was, you know, on the wrong track there. So this idea kind of the explanation for the acceleration in the universe is this cosmological constant, after all, this repulsive force. So continuing to drive the acceleration in the universe. So kind of they've got a couple names for it here. The cosmological constant, as that name applies, means that the strength of the force does not change over time. It stays constant. That's the cosmological constant, one of them. The other one that they're thinking about, a possible energy here, could change strength over time. So the repulsive force could change strength over time, and they call that one quintessence. So this idea that there is this repulsive force in the universe that's driving the acceleration of the expansion could either be called the cosmological constant or the quintessence, right? So either constant strength or quintessence changing in strength over time. So two kind of names that we could potentially use to describe this force, constant or changing. Okay. So with this either cosmological constant or quintessence, so it is some form of repulsive energy spread throughout the universe, right, through the space, that they are referring to this as dark energy. So it is a repulsive force of energy in the universe, and that this energy is what is driving the acceleration of the universe. Okay? And it doesn't contribute to the formation of starlight or the cosmic microwave background radiation in there. So could the dark energy make up the rest of this critical density that we needed? So what kind of prompted them to think about dark energy was that more distant supernova had been determined to be, you know, a bit brighter than expected, a little fainter than they would have thought. So this kind of prompted them that, oh, there was this extra acceleration happening in there because of the dark energy in there. It kind of seemed to 6 billion years ago, the universe kind of shifted gears from decelerating to accelerating. So they feel like that study of those supernova, how they dim over time, whether they're appearing a little brighter or they're appearing a little fainter, really does help support this idea of the extra kind of inflation. The inflationary Big Bang theory, they're using that to really kind of cinch their new theory that they've tweaked just a little bit in there. And dark energy can help us understand the lack of curvature of space-time. So makes a specific prediction. Dark energy seems to confirm that prediction. So energy and matter are equivalent. That's Einstein's equation in there. So dark energy is equivalent to mass spread throughout space. And so we can use that to add into our critical density, okay? And so that's kind of what their idea is. So they're taking the normal matter plus the dark matter, that was what, about 30% together. And then dark energy seems to make up the other about 2/3, okay, of the critical density. And so, amazingly, when you include the dark energy, the total mass plus energy of the universe, the density, the actual density of the universe, seems to equal the critical density, making our universe flat, zero curvature. So the universe is flat, was the conclusion of this. All right, so, and so they're thinking, well, the universe is ruled by gravity, or is it ruled by this repulsive force? That's kind of the thing as to what might be our future sort of thing. Power of dark energy dominates gravity. You know, even an enclosed universe might just expand forever and ever, because the repulsive force kind of is dominating over the contractive force of gravity. So they kind of are trying to think of the fate of the universe in here. And they actually have, you know, whether or not, oh, at some point gravity is going to take over and it's going to begin to contract everything in a big crunch kind of thing. Or is the, you know, cosmological constant that drives the acceleration just going to, you know, be constant, and then universe just expands forever and ever, galaxies get farther and farther away, eventually all those stars die out, and then it's just going to expand in darkness kind of thing forever. And then, you know, or is that expansion going to accelerate, right? The quintessence version of the cosmological dark energy. And then like a big rip kind of thing would happen. And so they're just still grappling with a lot of these theories on the future, the fate of the universe. So yeah, would it be a big rip? They don't think that's going to happen. You know, probably no big rip. They're pretty sure that the cosmological constant of dark energy is the one over the quintessence for that. And there was a huge study, and in 2018 they actually got the prize, breakthrough prize in physics for it. But they have a little bit of these observations I want to show you. Where'd they go? Some irregularities in the cosmic microwave background radiation. This is part of the Wilkinson anisotropy probe study that they mention in here, that background radiation is very isotropic, kind of looks the same. But when the average intensity is subtracted from each little spot on the sky, there were just some very small irregularities. Some of these looked a tiny bit hotter and brighter than other spots, so they put forth their 3 models here of what they would predict those variations would look like. And so here we have our closed model, okay, and that they predicted those spots, those variations would be a little larger than a degree, angle of a degree. If we had our flat model universe, it seemed like the little spots would be exactly about 1 degree in diameter. And this one here in our open model, kind of that saddle shape look to it, that the spots would be less than 1 degree of an angle. And this is like the actual observed data. So when you take a look at the actual observed data and you try to compare it to the predicted values according to those 3 models in there, I don't know what you think, but what I see is the actual looks very close to the flat model universe. So this was something from that study that they did see that was one thing that did help us to come to the realization that, yeah, we do have a flat model for the universe. It matched best. And so they're kind of plotting out the curves here. This blue line would be what an open universe would be. The red line here is what it would be if the flat universe was it, and you can see that the points are following the flat universe model more so. Yeah, really not much on the open universe there at all. So seeing how common those different sized irregularities were in each of the different models in there. And so it did show that it really did fit the flat model best. Okay, and so that was actually a very good of this WMAP, the Wilkinson microwave anisotropy probe study that they had. Okay, and it actually gave us a lot more data on the universe as well. I mean, it answered like a ton of questions, so this is why they got that prize in 2018 of the breakthrough prize in physics, because it pinned down many things that the age of the universe derived from that data, so we can hone that down. We've been saying about 14 billion years, but now we can tweak that and hone into 13.7 billion years. And furthermore, they were able to figure out that the amount of matter, normal matter, dark matter, okay, so the universe contains about 4% of the baryonic or the normal matter, 23% dark matter, and 73% of this dark energy, that repulsive force. And furthermore, that they do feel that the cosmological constant variety of dark energy is the one you want to go with, the constant strength over time. So it's not changing its strength over time. Okay. Oh, and the Hubble constant was confirmed, 71, plus or minus there, 4 kilometers per second per megaparsec. Inflationary theory of the Big Bang theory was confirmed as well. I'm telling you, it answered so many questions in there. Data supported the cosmological constant version of dark energy, although they can't rule out quintessence, but I think they have ruled it out. And dark matter needs to be the cold variety of dark matter, meaning slowly moving, so that things could clump in order to give us our, our galaxies and our quasars and clusters and all that. So just so many things that revolutionized cosmology in this one study here. And so, but you don't want to get too excited, right? Because, don't get too premature here, because we don't understand dark matter, right? And, that was 23% of the universe. And furthermore, we don't have a grip on dark energy, which was 73%. of the universe. So over 95% of the universe is still not understood, right? So we do make headways, and we do build theories, and we do go after the actual observational data as well. So yes, the kind of that, I'm going to write that up there, the Wilkinson microwave, all abbreviated here, but the Wilkinson microwave anisotropy probe, okay, the WMAP, revealed evidence on many things. It suggests the universe is flat. That it is infinite. And accelerating. In its expansion. And plus, you know, it gave us the details on the cosmological constant for dark energy, the amounts of normal matter, dark matter, and dark energy, and in the universe, Hubble's constant, right? It nailed down just so many things. 13.7 billion years for the age of the universe, we can write that. So that the universe did have a beginning, and they're just kind of trying to think about the futures, you know, is it going to continue to just go expand off into darkness kind of thing? Will it accelerate in its expansion? They almost think it's going to be the steady state, though, as we kind of go through. So an incredible study, the Wilkinson microwave anisotropy probe study that they did, and of course that team did in 2018 get the breakthrough prize in physics for their work, and it was revolutionary for cosmology, the study of the universe as a whole. So that does conclude our unit on the galaxies and modern cosmology in the 21st century unit. And so you want to make sure you have your study guide handy and that you're going through all your bullets, and make sure that if you have any questions to get with me, and we will see you for our next unit where we're going to rein it back in. Here we've been out clearing the universe. Now we're going to bring it back into our solar system and take a look at the planets, the inner and the outer planets, and kind of the origin of our solar system. So we will see you next time. Thank you.